Welcome to this video on the electric field part 7, which is titled the electric potential. Now the electric potential is probably one of the concepts that is most foreign to students when they start studying electromagnetism. The electric field makes sense because we know things about the gravitational field and that, but electric potential just seems a little elusive. But we're hopefully going to demystify it in this video because it's a very important part of what we've done. Also, this video plays into a lot of what we talked about in video 4. So if you have a chance or forgot what information was in video 4, you might want to go back and check that out again. So jumping right into it, we look at these two different scenarios that I have set up here. Now you can imagine these are metal plates that we're looking at from the side, right? So that you might imagine them being kind of, if I was to sketch this out three-dimensionally, something that looked somewhat like that. But we're just looking at these two metal plates from the side, and you can see that one of the plates is positively charged and the other plate is negatively charged. And in the situation here on the right, I have it flipped where the top plate is positive and the bottom is negative. So I'm going to go ahead and sketch in the field lines first. Now we know that the field lines point away from positive towards negative, and so we get something that looks kind of like this. Now I'm just drawing 4 field lines, but there could be more. Now in this circumstance over here, we see that the field is directed down toward the bottom of the screen. And so in both cases here, we have an electric field that we would refer to as a uniform electric field. And that's uniform because the charge is evenly spread out along each of these plates, and because I have the two plates set up in this way, I know that the field should stay the same, because if it were getting weaker this way, it would start getting stronger this way, and so we have this balanced field. Visually, we know that it's at a uniform or constant because the field lines neither converge nor diverge, and so they're staying the same distance apart, so the same density, and therefore represents the same situation. Now in video 4 we talked about if I had a ball that had a charge on it, and let's put a positive charge on this ball. Well, we know that this positive charge is going to naturally get pushed away from this and be attracted to this, right? So the field would do work on it, moving it up this way. So we refer to that as the work being done in this case is the amount of electrostatic force being exerted times the displacement. Now, of course, we came up with the expression for the force, which was Q times E times delta X. And we're going to see how this will play into what we've been talking about from before. Now the same thing would happen here. If I put a positive charge in here, it would naturally want to move this way, and I could calculate the amount of work that the field does to naturally pull it. But now we're going to talk about where the electric potential energy between the charge and the plates would be the greatest. Well, remember that the potential energy, the electrical potential energy, is going to be greatest at the point where the configuration is least likely to naturally occur. And so this positive charge is least likely to be found next to the positive plate, and it's also least likely to be found away from the negative plate. So this position right here where it's at, if I could draw a dashed line all the way across here and say at any position across here, that is the least likely place that it's going to be. Now, at this basic configuration right here, with this delta X value, right, or we could describe this as this R value, we'd say at that position, the charged particle and the plate, or the charged particle and this plate, have the highest electric potential energy that they could have in this space between here. Same thing goes here. If I put this positive charge here, anywhere nearer to the positive would be the greatest place. Now this term electric potential is different from the term electric potential energy. So if I'm writing electric potential energy, I usually use a U, and I say that this stands for electric potential, and the key additional term here is energy. But in this video, we're talking about electric potential, and that is symbolized with the uppercase V sub EL, and this is just described as the electric potential. So when we describe electric potential, what we're doing is we're actually erasing the object from the scenario, and what we're saying is that just based on location, so anywhere along this band, or I could probably draw it a lot closer now that I don't have the object, but anywhere along this band over here is said to be a location of high potential. So it's describing the location and not the actual energy between the charges. So if electrical potential energy is measured in joules, like all other forms of work and energy, electric potential is measured in joules per coulomb. So this is very analogous to the electric field, which is measured in newtons per coulomb, because it just described a location. And when I actually multiplied the newtons per coulomb by a number of coulombs, I could actually get the force, which was more analogous to this. So when I only have a field and I pick a location in the field, I can choose many different places. What I say is that location has an electric potential. So I might describe this potential here as VEL, and I could say that this is the highest potential in the field. Now remember, it's always judged off of if there were a positive charge that was going to be placed there, not a negative charge. So by convention, and this is very, very important, by convention we have to always know that the place of high potential is defined as the more positive location. So the highest potential place in a field is the more positive place, and therefore the negative place, or the more negative place, will be considered the low potential place. So in this diagram on the right here, this top plate would be described as the place of high potential, and the plate down here would be described as the place of low potential. Now the field is uniform, but the potential is not, because as I move locations down and down closer to this negative, or if I were in this diagram, as I move closer to this negative, the potential becomes lower. Now what that's referring to, remember, is that a positive charge placed there would have a lower amount of potential energy due to that natural configuration, rather than if I placed it here. Now what if we had a negative charge? Because after all, the things that move around the most are electrons. So what if I placed an electron at this location right here? Well, that is still considered to be a place of high potential, but we know that an electron will naturally want to be at a place of high potential because it is negatively charged. So that's sometimes a little bit confusing for people, because we always naturally talk about things going naturally from high to low potential, and that is the convention in electricity, because we always assumed the little moving charges were positive, like to be discussed in video 4. But because we know that electrons are negative, we say that electrons naturally move from places of low potential to places of high potential, whereas positive charges always move from places of high potential to places of low potential. Now, when two like charges are together, that is still a place where there's high potential energy, right, between the configurations. So this electron over here next to the high plate, yes, it's in a place of high potential, but there is a higher potential energy if the electron was moved over here. So it's a little bit confusing because of the terminology that the positive is always considered the place of high potential and the negative low potential, even though we would say the opposite for the potential energy of this configuration. Now what I'm going to do over here is look at a comparison again between the gravitational field and the electric field. And so if I draw in gravitational field lines, remember these will have to point towards the Earth, we can clearly see that as I move a little mass, so I'll place a mass right here, as I move a mass further away against the field lines, notice that the gravitational field and the displacement are opposite one another. That location where it's moving is a place of higher potential than being right over here. Now for the charge systems, that's the opposite. So for a positive charge, because the field lines point outwards like this, we say that a positive charge, because remember everything's judged off of a positive test charge, a higher place of potential would be closer and a lower place of potential would be farther away. Now this point all the way around, just like with the electric field, we'd say that at the same radius position, at any point along this curve, we would say that the potential is equal to the constant, again, 4 pi epsilon naught, or 1 over 4 pi epsilon naught, times q, because the strength of the charge will determine the potential at whichever point, over r. Now it's not r squared, it's just r, and we can see that there's that very close relationship because I could also calculate the electric field anywhere on this point, but this would be a value of 1 over 4 pi epsilon naught times q over r squared, and we'll get into why that relationship is the way it is in a little bit. Now, I'm going to leave you with one idea here, or one challenge, I should say, and I would like you to try to figure this out for yourself. And then when the next video, we'll come back and take a look at it. This equation just describes the position, right? It just describes this location within this electric field that we describe in joules per coulomb. Obviously, the E describes the strength of the field in newtons per coulomb. I want you to try to figure out what would be an equation for the electric potential energy based on if I actually now took this location and placed a little positive test charge at that location. How would I manipulate this equation to show the actual amount of energy between the source and the test charge? So how would I describe the energy between those two things? A way that you might think about it, a little hint, is how much work would it take to move the two, or to move one of them from the surface of the source out here, or vice versa back. Think about that, and when we come back in the next video, we will take a look at it.